Yeah, thank you for these papers. I was thinking a lot about just something that Grace mentioned very briefly about how noise comes from the agents sometimes. The noise isn't always an environmental problem. And that seems like introspection is kind of with that same question. So like, to what degree do you think the literature has already like distinguished, I guess, noise that the agent produces from the signals it wants to focus on? Does that make sense?
Yeah, honestly, I can't comment on what the literature has said. I'm still just kind of digging into this topic in terms of literature search and that kind of thing.
Well, I mean, do you have any like thoughts specifically connecting to that comment of Grace's?
Sure. So, I mean, you know, I gave you this whole kind of laundry list of different measures that we might look at, and I kind of had it separated into these three categories. But some of these were related to the learning process, some of them were related to the environment, and to the experience and that kind of thing. And that's a bit misleading because you're absolutely right. These things are all kind of tied up. The environment affects how the robot behaves, it affects the learning process. Those learning algorithms affect the kinds of decisions you make about what more data you want to acquire and these kind of things. So they're not that well separated, and they are kind of bound together. And so I still need to figure out exactly how much differentiation I can get with those.
Hi, I have a question about, from the introspection perspective, have you seen how it actually contributes towards increasing or improving the rate of convergence of the overall model to an optimal behavior?
I haven't done experiments yet, so this is kind of the next step, is to get this up and running and start looking at really how this makes sense in decision-making processes. Yeah.
Okay. Slightly more extended question. I'm not sure to what extent people would agree that the robots generally are going to operate on an OODA loop type principle. I mean, but along those lines, there's effects of uncertainty and novelty. Uncertainty generally is going to operate at the decide level where you have to make a decision. You know, I don't know enough about either what the object is or exactly where I am, so I may have to explore, versus novelty that's generally going to appear at the observed level and cause you to reorient. I mean, you'll have sort of an immediate response. So my question is, with those two elements, uncertainty and novelty, do you have to do special things in order to deal with it?
I'm not sure that I'm entirely clear of how well those two concepts are separated.
Well, uncertainty is, you're approaching an object, you don't know what it is.
Right.
And so you either have to make a decision to explore more or to circumvent it, or whatever you're going to do, whereas novelty, there's something that appears suddenly, you have to react to it. Say you have to avoid a collision with it, whatever.
Yeah,
it's sort of...
You're talking about the same object, just uncertainty is prior and novelty is posterior.
Okay. Okay. So then what's the question then with those two, if you have those two?
Just how is that going to impact your reasoning processes? I mean, like, do you have breaks in the induction? Do you like switch off to an entirely different path?
Right. Yeah, honestly, I don't think I can give you a great answer on that. ideally, I would imagine, like, kind of what I'm trying to argue for too is that you don't treat these things specially. You allow your system to make all sorts of measures and models of what's going on. And then, I'm coming from a reinforcement learning background, and so it takes these bits of data, whether they're internal or external, or uncertainty or novelty, and you simply take them as part of your state space, you take them as part of your model, and you figure out the best policy to act in those situations. I want to hand code any sort of particular way of responding to either of those.
With that, I just want to mention, I think part of what Ray was thinking about was if you rank your programs in order of likelihood, that I think you're talking about sort of like a black swan event, and that if you have a full ranking of programs and you weight them, you may be able to answer that question sort of like a Laplacian thing. Maybe you can talk about it afterwards. I can show you some of what Ray was writing about in terms of the problem of the black swan and how you can anticipate it as part of a coherent thing. It's not a separate thing.
Yeah, that makes sense. It's the solution of the Blackstone or White Raven problem. And actually, Hutter has a paper about it. It's similar, but the thing is, there's a lot of background knowledge, right? So you know a lot of things about animals, genetics, how they can mutate, so you can actually predict that there could be a mutation somewhere and you could have a bird with a different color, right? So if you're going to have that problem of induction, if and only if you have no background knowledge whatsoever.
One other quick thing is that since what Ray was interested is measurement, so that you could actually measure into the future rather than just measuring here, measure here, and weight the likelihood of these future things. And by the correct weighting, you can have some information about a black swan. And he did a lecture on that is on the website.
So, Arthur, I have two questions for you. The one is, how does your approach change if the features are not independent? Have you done any work on that? How would it affect that? And the second question is, do you have any practical examples, any tests that you actually ran, and what kind of speed improvement you actually found, if you have done any kind of practical tests?
So, concerning the not independent features, so the math actually shows that there is always such a set. If an object is, or if a string is incrementally compressible, then there is such a set of features that are independent. Of course, the set is not unique. It's like it makes an orthogonal basis, but the basis is not unique, like in linear algebra. You can have a different set of features that will also be mutually independent, but they might be dependent of the first set of features that you have chosen. So, of course, the number of possible features is infinite, but such sets do exist that are independent of each other. I mean, intuitively, they make up different sort of equivalent representations of your object that you're describing. So, and the second question was about the practical implementation. Yeah, I quickly referred to my last year's AGI publication, where I actually executed all 1, 2, and 3 state Turing machines and generated billions of strings, and then applied a similar method that incrementally compresses them, and it arrives at almost the shortest descriptions of them if you measure shortest by resource-bounded learning complexity. And yeah, it does seem to work and much faster than if you try to look for a solution in a non-incremental way. So yeah, in a sort of, I mean, it's not kind of realistically useful now, but it does work in practice, and yeah. So
I have a question for Mr. Arthur. Do you think, could you relate in any way the Fourier decomposition and the orthogonal basis that you just talked about? Is there any relation whatsoever?
the Fourier decomposition, well, is it possible to make a Fourier decomposition of the space of programs?
Something like that?
Well, I mean, how can I relate it to something that doesn't exist? I mean, it is a type of decomposition, and it decomposes the problem, and that's why it speeds up Levin search by such a big amount. To make it really useful, you'd have to speed things up even more, and I pointed to the possibility. Let's say you have the whole universe encoded as binary string. In order to find a description of it, you wouldn't try to find a program that generates the description of, generates the encoding of the whole universe. You would just start describing, you know, this little object and then that little object. You basically partition your whole string into little pieces and try to compress them piece by piece.
Piecewise.
Yes. And how to do that, and to derive theoretical guarantees for that, this will be a very interesting future work, and that would speed up things even more.
I don't think that can work in general, can it? I mean, if you have a general program, you can't, in general, decompose it hierarchically into pieces. I mean, that's sort of a special case.
Hierarchically, in terms of first finding a partition of it and then go, I don't know, because this is future work.
Sorry,
do it incrementally.
Sorry, but we already have done such work with the hierarchical decomposition.
We have what?
We have already done such work, and we have publications on this. And we also obtained similar speed up as in your case, but not in an incremental way. So it's not absolutely future work. It's at least partially already.
So hierarchical but not incremental?
Yes. Well, it's not incremental in your sense, but I guess we can discuss it.
I'm curious to find out about it, because I don't know what you mean.
Yeah, we will discuss it during the coffee break. We have much more questions.
My question to Eray.
All right.
In terms of the physical limits of induction, you provided one number, 370 something, and you said that represents the limits for this universe. And you say this universe, which parameters of this universe are relevant for that composition, for that computation? Can you provide some insight?
So you have to see the paper. It explains there. It's referring to the physical limits of computation work. Marlos Levitin bound, and that stuff. The safe flows work. So there are some physical measures, and it derives from there. It's in the paper.
Is it like, you know, the size of the universe and things like that?
No. It's about the how many computational operations you can make with a given for a fixed energy. So it's something like that. I can't really explain it without equations.
So if the universe is not finite, what then?
The universe is not. It's not relevant to us because there is we're not going to get any signals from outside of the universe.
Just maybe
so it doesn't matter.
Energy may be created.
Yeah. So, but it doesn't matter because no stochastic source you can observe will lie beyond the observable universe. So it really doesn't matter if the universe is infinite in extent or not. So that's pretty obvious, right? Because Einstein's theory is correct.
Couldn't there be quantum entanglement when things beyond beyond our observability to the speed of light?
Yeah, so you're not going to, that still isn't going to matter. It could contribute to the stochasticity of the phenomena, but you're not going to get any order out of it. So it's still the same thing. It's not going. It won't matter. Okay.
Question for Dr. Eray. Should I say that right? Eray. Well, anyway, I'm not used to data information coming out in units of meters. What towards the end, again, from the famous number of 400 bits, it's going to be famous shortly.
Yeah.
You
So
said
we got the same number
if
again.
the volume is 1 meter.
Huh?
You said
Logical volume of computation.
The bit string describing the universe. The logical
No.
volume of
It
what?
means any computer that's going to have a space-time volume of computation that's smaller than 1 meter cubed times second, right? So it's not for very large computations, but for reasonably sized computations, that is the case.
So you're setting a smallish limit?
No, it's okay. So the logical volume of computation was with respect to the stochastic source there, I think, if I remember correctly, and that means we're not considering very large sources. We're not considering very large, physically complex sources actually. But so there's a condition. If you remove that condition, that number could change there. I didn't really analyze. It's just an example, right? So it's just an example to show that you can obtain some numbers if you substitute them. So it's not just theory, but it's not a theory that's applicable to the real world.
This is a question for you, right? You introduced the concept of stochastic logical depth,
Yeah.
extending Bennett's concept, and you say that it involves accurately simulating the stochastic source. Can
Yeah,
you say
so
more on what you mean by accuracy?
Well, what do I mean by it? Well, since induction will work only with computable PDFs, right? So that if it's computable, it means you can simulate it exactly. Accurate means exact in this context.
And how is it defined?
Exact means like it yields exactly the same probabilities, man. So it's yielding, of course, computable reals, right? And yeah.
We have time for a few more questions.
But that's maybe not so obvious. I thought it was very obvious, so.
My question is to Ms. Solomonoff. I'm just wondering, what was Ray's take on transfer learning with respect to Solomonoff induction?
When you're talking about transfer learning, can you be a little more specific?
Incremental learning, the 8-9 paper, and
You mean like concept nets?
no, it's the stuff I talked about the other day. So,
Let's see. Well, he would have that you can take parts of programs and pieces of concepts and add them together. You can combine them to solve a future problem using the building blocks for problems. And he would use that with Levin search to quantify steps in the learning, so that you might have you might start with one program that you found, and you can find regularities in that program to build. And say this guy finds one program and this guy finds a program in a certain time length, in like a computational cost time length, and you can take these different parts of programs and maybe combine them into a smaller program. But you would want to keep the idea of ranking of the different programs, because some of the parts of the programs might end up with different size ratio, different sizes than other ones that you combine. I'm afraid that's not very clear, but it's the idea is to combine the different bits of things and to rank the different bits of things in a hierarchical order. And with Ray, I think one thing that frequently gets left out is that he's really interested in ratios of things, so that you don't just necessarily find the smallest thing. You're not just looking for an Occam's razor, which is why you can find different, as long as you can kind of measure the different concepts to combine them, and then you do find smaller, but you want to keep a ranking so that you can go back to a lower concept. And if, say, this concept didn't work, you could go back to an earlier thing and build from lower steps. And we can talk more about it, and maybe I can show you some of the lectures that he had, because he can explain it in a less poetic way.
May I explain it? It's my field of study. It's Solomonoff did say that incremental learning is absolutely essential. He never suggested that a non-incremental thing would reach high levels of intelligence. And that's why he explicitly wrote this as an important open problem. And he had many suggestions. And the other thing that you talked about is, I mean, in the standard theory, we call that base factor, right? So that's how, that's the scientific right way to compare two competing hypotheses. You should use the base factor. And base factor and those ratios are basically the same thing. And the other thing is we are probably going to need very sophisticated solutions to make induction approximations work in the real world for incremental learning. Without incremental, it just won't work at all.
Okay, it's time for coffee break, but probably we can have one more very short question, if it is very short.
I don't know if I'm sure. Did somebody give an intuitive explanation of what Levin search is?
Well, you represent programs as binary strings that are executed by a universal Turing machine. And you can order those binary strings by length and lexicographical. So then you start executing them one by one. And you attribute the time of execution. It depends on the length of the program. So you execute a shorter program for a longer time and a longer program for a shorter time. And
the important thing is that the whole running time is allocated in proportion to the a priori probability of a candidate program. So that's Levin search. And it is necessarily so. And since there is a halting problem, you can't just allocate this, but you have to start with a small time limit, and then you double this time limit in each iteration, and so that you this watchdog policy overcomes the halting problem in this case.
Essentially, you're setting a time limit, and you do your trial programs in order of the increasing, as Eray is saying.
In proportion to
but it's
a
not,
probability.
But it's not necessarily just the length of the program, because that's just with binary strings, and it's the computational cost. So that sometimes you might, instead of having just a short program, maybe a longer one is actually faster than a short one, so that it's allowed to have more time too, because it was faster. So it's a way of ranking programs, and I think they just use the length and the computational cost. But you could have other measures of how fast your program could do different aspects of your program that could keep it within this time bound. But if you search in all the programs don't find anything, then you can raise the time and you start your search over. But you have to be careful when you start the search over, because you don't want to do the same thing that you did last time. So you need to, you're going through the programs, you need to change things a little bit. And I'm not sure how Ray was able to do that, but it is important, because you don't want to learn the same things over again. You want to have some way of knowing what you did, because it's very important with learning to remember things. And a lot of these searches, they start and they find the thing and then they go back and they forgot the whole thing. So part of Ray's work with 11 search is how to change things or save things in order for the future search. It's all part of trying to make it more and more practical. It just still isn't.
That's called adaptive level search. So if you find out the ordered optimal problem solver, that's something very simple you can just understand.
Okay, let's thank again.